Hey all, sorry for the people during fifth hour today that got kicked out of the Zoom or the Zoom didn't work at all, whatever that means. So I'm just gonna go through what I went through at the beginning of class in this short little video. So if you feel comfortable with the content in this notes, then feel free. You don't have to watch it, just for those people that weren't able to hear it live because of the error in the Zoom call. So what we were doing today in class was we're just introducing all of our parent functions, and I walked through a few important details about each of them. So the first thing that we did together was make sure that we named every one of them. So the naming at this point, you could probably just look up, but I just wanted to talk about the names of them so we had all of the appropriate titles, so we all talked about the same thing. I then just mentioned that this table is what your job is going to be. So you have to create a T-chart of tables. And when we were doing that though, we want you to do this without a calculator. And the reason we want you to do it without a calculator is the values that we've put in the table are selected just for that function. So you can work with that function better and know what that function does. What do you put in? What does it do to it? And then what comes out? So I do want you to create a T-table of values on your own. And the next thing we talked about then is if you are taking and making the T-chart, then you will make a graph of those points. And as we're saying, you're only plotting a few points, 1, 2, 3, 4, 5, 6, 7 points. But we snuck up here that we're gonna guarantee that these are all functions. So here we're gonna say that they're continuous too. And we just gave us permission to connect the dots right away. So what we're saying in this opening kind of paragraph here is we've given you nice values that you can do without a calculator to help you interact with the machine. But also the points that we've chosen, if you connect the dots, we'll make sure to make the proper shape. So what we did for everyone is I wanted to practice them just the domain and how we could calculate the domain without a graph. And we just thought about what this function does, right? So we reminded ourselves that the input value is in here, and then this is what it does to that input. In other words, how does it calculate the output value? So in this, I can see it just takes in that number, and whatever number it takes in, it's just gonna square that same number. So we thought about this as a machine. If I'm going to put a number into the machine and that number is just going to be squared, are there any numbers that I can't square? Or conversely, what numbers am I allowed to square? So we had this notion that for the domain values, all the x values that I can plug in are going to belong to the real numbers. And again, this is our symbol for saying that x is all the real numbers. So we thought about the domain for each one of them, and then I just stated that it would be your job after you complete the work to discuss the range. So I'm going to do that for every function. For a few functions, I had some background information and explanation. So this one was our cubic function. Again, as I mentioned in class, just trying to mirror exactly what I did in class. This is going to be your responsibility to fill out the T-chart. Once you have the T-chart, you then plot those points. Once you have the points plotted, then you can connect them with a dot. Let's think about the domain for this one though. So the domain of this function, what this function is going to do, and I just draw this little function machine, it's going to take in an x value, and it tells us that it's just going to cube that x value to give us an output. So I'm thinking to myself, either A, what numbers am I allowed to cube? Or in other words, what numbers can I not cube? And we said we could cube any number, right? You can multiply any number by itself 3 times. So our domain, again, is all the x's of the real numbers. We'll move on to the square root, and the square root function did have a lot of background information, along with our cube root function. I just wanted to make sure we understood what those functions were doing with the inputs. So we remind ourselves, first I think of this as a function machine. So I'm going to put in an x value, right, because I can see x is the input, and it tells me whatever number you put here, we're just going to take the square root of it. So then we took a moment just to remind ourselves of what that square root is. So if I'm taking the square root of a number, what we're thinking about is what number times itself twice would give us the number under the square root. So that's why, as an example, the square root of 9 is equal to 3. And the reason why that's true is because if we thought about what number would I multiply by itself twice, if I put a 3 in both boxes, 3 times 3 is equal to 9, which is why the answer is just what's in one of those boxes. We then talked about right away, if we thought about the square root of something, I'm just going to do another example here, like -9, we run into a problem. Because I'd be asking myself, what number would I multiply by itself twice to get a negative number? And we realized that if I started with a negative times a negative would equal a +9, not a -9. So it wasn't that. And of course, we just said 3 times 3 was equal to regular 9. So none of these are negative 9. Because if we're going to multiply something twice in a row, whether it be a negative and a negative or a positive and a positive, it's always going to come out as a positive number. So here, when we're thinking about the domain, then I know that I can't take the square root of a negative. If I thought about this, what numbers am I allowed to take the square root of? Or maybe on this one, what numbers can I not? Well, I can't take the square root of any negative numbers. So the values that I plug into my function machine, all the values of x for sure have to be bigger than 0. And then we thought about 0, and we could take the square root of 0, so we included that in our domain. So in the table here, we just wanted you to know that those values were undefined. So in your table, you can just write that word undefined. We then moved on to the cubed root. We just talked about that as a function. We said, well, it's really the same thing, right? When I think about the cubed root of x, rather than writing 2 boxes for the square or the second root, we would just write this box 3 times. So here we compared, well, what is it going to look like for positives and negatives? So for instance, our first example was we looked at the cubed root of negative 27. If I had to multiply something 3 times in a row to get a negative, I know it'd be 3 negatives in a row because 3 negatives multiply together to be a negative. So then what would I multiply by itself 3 times to get 27? Well, that's negative 3. So when we're working with the cubed roots, we can use negative numbers. And we'll just do an example of the positive too, right? If I was asking myself what times itself 3 times was positive 27, well, if I want a positive answer, I can start with just all positive numbers, because if I have an odd number of positives, it comes out positive. If I have an odd number of negatives, it'll come out negative. So we use this example for us to see that when we're using the cubed root function, we could actually input any number. We could use a negative or a positive because we have an odd number of boxes. So our domain here were all the x's, that as long as they were a real number. Number 5 was really easy. It's just our linear relationship. We just wanted to make sure we understood what the function machine was telling us. So with this one, it says, whatever number you are going to put in as the input, you just spit that out as the output. So in other words, we're doing nothing. So even though it's an easy example, we still try to fit it into that frame of mind by asking ourselves, what numbers am I allowed to do nothing to? Well, I can do that to any number. If I put something into the machine and it's just going to fall out, my domain for this function is going to be any real number. The absolute value function, what we talked about was, we're really familiar with that from Algebra 1. So we just took a moment to think about the function machine before we went into our table and completed that. We just asked ourselves, what numbers are we allowed? If I'm going to put in an x value, if I plug in x to give me the answer, it's just going to take the absolute value of that. So what numbers am I allowed to take the absolute value of? Any of them. Or conversely, what numbers can I not take the absolute value? I can't think of any. So we're saying that for the absolute value, we can plug in any number we want. This was our exponential function. I don't need to write function, just our exponential. And we just reminded ourselves of what was going on with the language. The big number on the bottom is the base, and the little number is the exponent. We just talked about how 2 would be the easiest base. If I had 1 to the power of x, just multiplying by 1 over and over, that's lame. And then I don't know how to multiply decimals, so the next easiest number was 2, which is why 2 to the x is our most basic exponential function. Now with this, I felt really confident for the most part with exponents. Like we all know what 2 to the 3rd power is, especially if we have to expand them. So when it came to the positive exponents, I wasn't too concerned, but I did want to take a moment to remind us of negative exponents. And what we had talked about with negative exponents is that negative exponents tell you to move the location of the base. And what we mean by location is we were looking at it as a fraction. We're looking at it, is it in the numerator already, or is it in the denominator already? Whatever position it's in, we need to move it. So we did some examples. So for instance, if we talk about 2 to the negative 1st power, first of all, we want to make it a fraction to work with negative exponents a little bit easier. So the easiest way to make it a fraction is just divide it by 1. Now what we notice is there's a negative exponent. So I view that as a verb. It's something that I need to do actively. So when I see where it is, it's currently located in the numerator of a fraction. It simply moves the location of that base. Then we talked about how you would have to take away the negative. And what I said was, think about the counter example. If you left the negative there, here, this negative would tell you to move it to the bottom. But then here, this negative would tell you to move it to the top. But that negative would tell you to move it to the bottom. So you'd get lost in this endless loop. So once you actually move, you've done that verb. You have done the negative. So after you do an operation, it goes away. Just like 3 plus 3 is 6. I've done this operation, so the sign goes away. And we just reminded ourselves that if we move something from the top or the bottom and nothing's left, we replace it with a 1. So 2 to the negative first power was 1/2. We compared that with another example, like let's say that was already on the bottom, like 1 over 2 to the negative third. Well, the 2 was already in the denominator, so I'd move it to the top. If there was already something there, we're just multiplying by what was there. And if I remove everything from the bottom, I just replace it with a 1. So then, the next thing we had talked about was just as a reminder, 2 to the 0 power is equal to 1. And the reason we reminded ourselves of that is because we know that 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8. So when I'm reading my table downward, I can see this clear pattern that I'm multiplying by 2. So if I was going backwards then, I was dividing by 2. So there's no choice, right? After I divide 2 by 2, I have to get to 1, which is why we made 2 to the 0 power equal to 1. And then the last thing we said here was on something like this, we should only use fractions. Because if we use decimals, they're not representative to us. But then I also like to see the pattern, right? If I kept dividing by 2, so on and so forth. So that was our exponential function, just a quick reminder of some stuff there. Moving on to our rational function. Oh, I'm sorry, I forgot the domain on this one. So we did talk about the domain on this one. And we had talked about in this pattern how we're really looking at the exponent as how many times have I multiplied by 2, right? So if I started here, if the exponent was 2, that means I've multiplied by 2 twice. We thought about the negative exponents as how many times have you divided by 2. So like for example, if we looked at 2 to the negative second, I've divided the denominator twice by 2. So we just asked ourselves, is there a limit on how many times you can multiply or divide by 2? And the answer there was no. We're going to have any input we want for the exponent into x. So we said x was all the real numbers. But then we also made sure to put in an asymptote right away at y equals 0. And then we just labeled that there's a horizontal asymptote. At the line y equals 0. Just so when we were drawing our graph, we knew never to cross that. The way we were thinking about that is if I started at 1 and I just kept dividing by 2, I'm never going to actually get to 0. I'm going to have a really, really, really small number, but whatever number you have, if I divide it by 2, it's just a little bit smaller, right? And that argument keeps going forever. So we're never actually going to get 0. As we moved on to our rational function, we knew right away that when we looked at this, if the input was x, we know that we cannot divide by x. So if we're thinking, or 0, excuse me. So if we're thinking about our function machine, it's going to take a number in, and it's going to take 1 and divide it by that number. The only number that we're not allowed to divide by is 0. So first of all, in our table, we wrote undefined. But then we went ahead and just looked at our domain right away. We knew that we could divide 1 by any number except 0. So we talked about a few different ways we could write that. You could say x is all the real numbers except 0. I'd accept if you wrote it like all the x's such that x is just not 0. Or a combination of the both and saying that x is a real number, it's just not 0. And to me, this is a hard one to write in our set notation. So as long as you're close, I'm going to give it to you. Now with this one, we put in our vertical asymptote at 0 because we know that we can't divide at 0. So there's a vertical asymptote at x equals 0. But then we also thought about our horizontal asymptote. We imagined the y value, or the output, just being 1 divided by a number. So we thought about, let's start with 1 candy bar. If I took 1 candy bar and divided it amongst one person, I get that 1 candy bar. If I split it amongst 2 people, everybody gets half. If I split it amongst 3, everybody gets a third. So the argument that we went through is, if I start with 1 candy bar and I'm just cutting it up into even-sized pieces, am I ever going to have no candy bar? And the answer there was no, because if I start with the candy bar and I'm just cutting it into pieces, my pieces might get really small, but they're never going to disappear. So there was also a horizontal asymptote at y equals 0. In other words, our output value is never going to be 0, because 1 divided by what number is 0. This last one was the weirdest for us, so I did get a little brief introduction before we jumped into number 9. I just kind of introduced that if we have this equation, x squared plus y squared is equal to r squared. That's a circle. It happens to be centered at 0, 0. You don't really need to know too much about it yet. And it has a radius of r squared, or of r, sorry. And in the formula, it's written as r squared though. So for example, if we look at x squared plus y squared is equal to 1, if r squared was equal to 1, then we know r was 1. So we said when we look at x squared plus y squared equals 1, it's just a circle with radius 1. So we drew a little picture of that, and we labeled the endpoints just to emphasize that it was centered here at 0, 0, and the radius was 1 unit in any direction. Now what we looked at then was, this is clearly not a function, and we're dealing with parent functions. Normally when we deal with functions, we like our y equals notation. So we talked about, what if I took this and I tried to convert it to our y equals notation? I'm just going to cover up my summary for a second because I'm going to run out of room. But what we did was just look at a circle. We knew this thing in purple was a circle, and then we manipulated it. We subtracted x squared from both sides. So we got y squared was equal to 1 minus x squared. Now in this case, we were solving. So when I'm undoing a square root, or when I'm undoing a square, I don't know if that person started with a positive or a negative. So if I'm undoing a square by solving, I have to use the plus or minus. We stopped and said this is a nice form to see why it's not a function, because the output, which is a y value, I don't know if it's the positive version or the negative version. So I'm thinking about that one input could have a positive output or a negative output. So we know it's not a function, but then we also chose to kind of split it up to see it as 2 parts. That means we could be talking about all the y values that are the positive version of that, or we could have been talking about all the y values that were the negative version of that. We then concluded to say, when I look at it like this just seems like one circle was split into 2 parts. Well, yes, because when we have one circle, we could view it as the lower part of the circle with all the y values that are negative, or we could view it as the top part of the circle where all the y values are positive. So whether I choose this version or this version, it's only half of the circle. So here, when we look at this one, somebody's asking us to only look at the positive version. So when I recognize that square root form, this is going to be a semicircle. It's going to be half of a circle. Now with this one, we said it was okay to use a calculator and decimals in our table. But we also just drew a picture together. So here the scale was a little too small, so I made every 4 boxes equal 1. And I only did it in the positive y-axis because this is a positive root. So we know because of the 1 that the radius was 1. So if I started here and I went 1 this way, I would end there. And if I went 1 this way, I would end there. And then when you fill in the rest of the dots, you will see that this is going to be a semicircle. But we had talked about there then was just the domain. If we know that my circle only has a radius of 1, my circle will never go outside of its own radius. So when I looked at the x values, I just pointed out how that looks very clearly like an and inequality. So we know that in a semicircle, the domain are all the x's between -1 and 1. If we didn't like the graphical approach to that, We then went back and just thought about the square root function. We know that the number under the square root can't be negative. So the most I can subtract from 1 would be 1. So that's what we did in class today. I also forgot to mention on this one here, only use fractions. Just on that last one, we're allowing to use decimals. So again, I apologize for the Zoom call, but again, then what we said was, hey, all you have to do for every one of them is go back and fill out your table, plot the points and connect them to make a function, and then tell me what the range is.